All right. Thank you very much for the assignments. So I posted one more assignment, but it's not one that's going to be collected. So it's just for practice. And what I intend to do, but it might take me a few days, is to write up my own solutions to those suggested problems, and then I'll just post them to the course website. Just because you're not getting, I mean, I know the solution manual is available. But the solutions I write tend to be a little more detailed. And then plus I'm not collecting and grading, so you're not getting feedback on those assignments. So I'll provide some solutions if you want to see those. Okay, so what we started to do is we just barely introduced spin last time. And we only looked at like a classical picture of what do we mean by spin. And the idea was if we take, for example, the Earth orbiting the sun, that has orbital angular momentum, but the Earth is also spinning about an axis that goes through approximately its poles. And we can chop up the Earth into these tiny little point-like masses and calculate the angular momentum of each of those point masses around this, I don't know, axis through the poles. And then we add up all those contributions. That's the spin angular momentum of the Earth. So some of the technical details we worked through for the hydrogen atom was trying to calculate the eigenvalues of the square of the total angular momentum and also of the z component. And what we discovered is that L squared has eigenvalues h bar squared j times j plus 1, where j can be integer or half integer. When we actually did the orbital angular momentum of the hydrogen atom, we found that only integer values were allowed. And so we would take for orbital angular momentum, j equals 0, 1, 2, 3, and so on. So these half integer solutions were not part of the orbital angular momentum. For the z component, we got m times h bar, or mj, where mj would run from minus j to minus j plus 1 to minus j plus 2, and so on, all the way up to j. And for orbital angular momentum, we then went ahead and found the actual eigenfunctions and found that they were exactly the same spherical harmonics that we got when solving for the wave function of the hydrogen atom. Okay, and so that's basically everything that sort of roughly where we ended last time. So what I'd like to do today is I'd like to talk about the electron spin. So, whoops, the electron also carries another form of angular momentum called spin. As far as we know, the electron is a fundamental particle, and it's a structureless point. And so we kind of think of it as this cloud of probability amplitude that surrounds the proton, and takes on some kind of shape depending on what state it's in. So it doesn't make sense to carry the analogy of the spinning Earth too far. The electron is not some kind of spinning object, and we shouldn't think of it that way. But by analogy with the Earth, it has two forms of angular momentum. One is the orbital angular momentum, and one is going to be the spin angular momentum. So its spin is an intrinsic angular momentum that's not associated with its motion in space. It's an intrinsic property, just like an electron has a charge and it has some mass. Like we didn't come up with any kind of fundamental derivation of where those came from. And so we're also not going to have some fundamental derivation of where the spin angular momentum originates from. So it's just like it has an intrinsic mass and charge. Okay, so we can work out some of the properties, and a lot of the properties that we've kind of developed for orbital angular momentum will translate directly to spin. So the algebra of spin is identical to that of orbital angular momentum. So we worked out a bunch of commutator relations, and those same relations hold for spin. So specifically, we had this kind of neat commutator relation where if I was to take the commutator of the x and y components of angular momentum, I would get the z component along with a factor of IH bar. And this works for any combination of x, y, and z inside this commutator, as long as we preserve, remember, the order of x, y, z. So if I put a y, z, I'm getting x on the outside. So I'd have a s, y, z equals IH bar sx. And then I just shift them over again, and I'll have let's see, what do we not have? We could have a zxy. So we could do an sz, sx is IH bar sy. Okay, good. So if we were to write down an eigenfunction type of equation for the S squared operator, this is an abstract representation of the eigenstates. So our electron has spin S and it has Z component of the spin, which has an eigenvalue M. So we can't write down like the spherical harmonics because that all depends on like position coordinates, and the spin has nothing to do with position of the electron in space. Okay, nevertheless, it's still true that the eigenvalue is just like we had before. Instead of h bar squared L times L plus 1, where L is a quantum number associated with orbital angular momentum, we'll have S times S plus 1, where S is a quantum number associated with spin angular momentum. And then to complete our eigenvalue equation, we have to write the eigenfunction. Okay, and the same thing we could do for the Z component. Remember, S squared and Sz have a common set of eigenfunctions, so these are the exact same eigenfunctions. And for the Z component, it was M that told us the value of the Z component, and we have this factor of H bar that we separated out. Okay, so just like we had raising and lowering operators for orbital angular momentum, we have them for spin angular momentum. So let's see. And if I was to take the Hermitian conjugate or adjoint Hermitian conjugate. I think you, if I remember right, you worked out the Hermitian conjugate of the L plus operator in maybe the assignment that you just handed in, and you showed that that gave the L minus. And so S plus becomes the S minus. And if I take the Hermitian conjugate of S minus, I'll get S plus. Okay, we could also take the Hermitian conjugate of the raising and lowering operators like this, and using these relations, we can show that this would be equal to Sx, and then we get minus plus I Sy. The reason we flip the sign is because when we take the Hermitian conjugate, it's like a transpose and a complex conjugate, and the complex conjugate changes the sign of the I that's out in front here. All right, good. So we had a very handy little relationship before for orbital angular momentum, and I want to bring that back. We were able to write S squared in terms of the raising and lowering operators. And the way it worked was like so. Whoops. So this was SZ squared plus minus, let's see, H bar SZ. This was sort of similar to something we did for, if you remember, the harmonic oscillator, where we wrote the Hamiltonian in terms of raising and lowering operators. Here, we've written our spin operators in terms of raising and lowering operators. Okay, so what I want to do is I want to consider the expectation value of this quantity. This is actually one of the questions in Griffiths. So we're going to solve one of the problems that he has. And in order to do this, what we'll do is we'll take this expression and sub it into here, and then that'll be relatively easy to work out because we've already written down what the eigenvalues for the Sz and S squared operators are. So what do we get? We're going to put in S squared minus Sz squared minus plus H bar Sz. And then we have to act on state Sm. Okay, so all we're doing is we're going to sub this into here. Okay. Well, S squared acting on this eigenstate has eigenvalue H bar squared, S plus 1. All right, and then we're going to get a minus. And then we have Sz acting on this state. Well, that's going to bring out an H bar m is the eigenvalue. But then we have two copies of that operator. So we get H bar times m twice. So we get H bar squared m squared. And then we're going to have a minus plus. There's an H bar here already. And then the Sz brings out an H bar m. So we get an m and an H bar squared. All right. But now these are all just numbers. These aren't operators anymore. So I can take these outside, and then I have eigenstate Sm, inner product with eigenstate Sm. If those are normalized, that's just going to be a 1. So this is just equal to H bar squared. Every term in here has an H bar squared, so I'm going to factor it out. And then we have a S plus 1 minus. Then we have m and m squared. So I can factor out 1m, and we'll get an m, and it should be plus or minus 1. Okay. So what I'd like to do is I'd like to go back to here. And we're getting pretty close to the result that we want to get. Um, so remember, we had this kind of trick that we could do where I could take this operator and act on the state to the right, or I could take this one and act on the state to the left. But to do that, I have to take the Hermitian conjugate of that operator. So let's write it out slowly. This would be equivalent to S minus plus acting on the state to the so let's see, how do I want to do this? Yeah, SM, I guess, is what we're going to have to do. And then we have S plus minus acting on state SM. So, but if we look back here, if this is S minus and I take the Hermitian conjugate, I get S plus. If it's S plus and I take the Hermitian conjugate, I get S minus. So I can just flip these signs over. And so this is equivalent to S plus minus on state SM, S plus minus on state SM. So this is going to give me lambda, whatever the eigenvalue is, times the state Sm again. So this one will give us lambda times state Sm. And then this one will give us the same thing. Maybe it's a lambda star Sm. Sorry, I got that wrong. This would be lambda star Sm. And so I'm going to get lambda times lambda star. That's the absolute square of lambda. But then I have these two eigenstates. They're identical. If they're normalized, they're going to give a 1. And so we end up with lambda squared. And this lambda squared must be equal to this quantity here. So these are equal. Everything in here is a real quantity, so I don't need to worry about the absolute square. That's just lambda squared. And the result is, therefore, lambda is h bar square root s plus 1 minus m plus or minus 1. And so this is the eigenvalue of the raising and lowering operator. So if we write this out carefully, we could write a new eigenvalue equation, s plus minus acting on state Sm is equal to h bar square root, s plus 1 minus m plus or minus 1. And then it's an eigenvalue state. Sorry, it's not quite an eigenvalue, is it? Because this, I shouldn't say that. The raising and lowering operator changes the value of m by plus 1 if it's the raising operator, minus 1 if it's the lowering operator. Okay, so that's one of the results. This works for orbital angular momentum as well. And so here it is. Okay. So what I'd like to do next is sort of get into some of the details that are specific to the spin of an electron, in particular in our hydrogen atom or just any free electron, in fact. All right. So if we think back, what we found is that orbital angular momentum has eigenfunctions given by the spherical harmonics, which we denoted by this y Lm theta phi, which required integer L. Spin, on the other hand, does not restrict the values of S. And so in particular, half integer S is allowed. So are integer values. And so we'll make a little table of some particles and the spin that's associated with them. So what we're allowed to have for a spin is S could be 0 or a half or 1 or 3 halves or and so on. And then M is going to go from minus S to minus S plus 1 all the way up to S minus 1 and then S. So some elementary particles, and this is not an exhaustive list of the elementary particles. It is a representative list. Okay, so there are some particles called the pi meson, and they have spin 0. So there are spin 0 particles, no spin angular momentum. But then there's a bunch of important ones that we are dealing with right now. There's the electron, there's the proton, and there's the neutron. These all are spin 1/2 particles. And so if you were to take the next part of this course, Physics 402, you'll eventually discuss some interactions between the spin of the electron and the proton in the hydrogen atom. And they'll make some very small corrections to the energy states that we've calculated, this minus 13.6 electron volts over n squared. But then there are still other particles. So a photon has spin 1. There's some so-called delta baryons. They have spin 3/2. There's the graviton, spin 2. And so that's some of our elementary particles. Just again, looking ahead to 402, if you were to take it. In fact, it's chapter 5, the next chapter. They talk about identical particles, and there's some really interesting and meaningful differences between spin 1/2 and spin integer particles. Particles with integer spin are called bosons, and particles with half integer spin, like the electron, proton, neutron, this delta baryon, they're called fermions. And the wave functions of half integer spin particles, fermions, have to be antisymmetric. That means if I had a 2-particle wave function and I swapped the 2 particles, the wave function would change sign. The probability density wouldn't change because of just that sign flip, because you have to square the wave function. On the other hand, these bosons with integer spin, they make, if you have a 2-particle wave function of bosons and you interchange the 2 particles, the wave function remains symmetric. It doesn't have a sign flip. That has really important consequences. What it means is that no 2 identical fermions with the same set of quantum numbers can be in the same state. And that is critically important in condensed matter physics. So The bosons with integer spin are more social particles. You can cool a system down so you get into the lowest energy state, and all of those bosons will crowd in together into the lowest ground energy state. Fermions, on the other hand, once you fill that ground state, you have to go to the next higher energy state. They can't be together. I'm more like a fermion, right? I like to have my own space and be myself. Photons are more like, our bosons are more like everyone together, let's be social and gather in together. Okay, good. Anyway, so that's just a little bit looking ahead. We're not going to do that in this course. All right. Um, the electron in the hydrogen atom can have any integer value of uh, let's say L for the orbital angular momentum. Um, okay, so we had these states where we had like L could be 0 or 1 or 2 or 3 and so on. And we called those different orbitals. Um, in contrast, S is fixed. So for electrons, S is equal to 1/2, and it doesn't change. All right. So what I'd like to do is I'd like to try to write down sort of a possible state for electrons. So we're going to write down the possible spin 1/2 states. So what we could have is, I'm going to call it a chi plus, and we'll see why it's chi plus relatively soon, is going to be, I'm going to write it down as 1/2, 1/2. And so what this represents is spin, S is 1/2, and it's always going to be 1/2. That's never going to change. The second number represents M, and M could be either minus S or plus S. It's minus 1/2 or plus 1/2. The reason we call this the chi plus state is because M is equal to plus 1/2. So this is M is equal to plus 1/2, and that's what we'll refer to as the spin up state. All right, and then we could have a chi minus. S is 1/2, that can't change, but we can change M. So this is S, this is M, and this is the M equals minus 1/2 state, which we'll call spin down. Okay. So if those are our two only eigenstates, what we should be able to do is we should be able to write any general spin state as a superposition of these two eigenstates. That's what we've been doing all term long for our eigenstates and expanding general wave functions in terms of components aligned with particular eigenstates. Okay, so consider a general spin state that would look like, we'll call it chi, and it's going to be some amount of the spin up state plus some amount of the spin down state. We have only two eigenstates, and so there's only two terms in our expansion. Okay, and so this is A is the coefficient that tells us kind of, if you like, the fraction of spin up in loose language, and this would be like the fraction spin down. Okay, so first, let's just take the inner product of this general state with itself. So if I was to take the inner product with itself, if it's normalized, I need this to be equal to 1. Okay, so we want to get 1. Let's see. So this is going to be equivalent to, whoops, chi plus b star, chi minus. Okay, so we have to take the Hermitian conjugate to flip the state around. When we do that, our coefficients, we take the complex conjugate. And then on the right, we just have our regular spin state, chi minus. Okay. And so let's just multiply this out. We'll get a squared chi plus chi plus. Plus, let's see, a star b chi plus chi minus. Plus b star a. What do we have? Chi minus chi plus. And then finally, we should have a b squared chi minus chi minus. All right. Like all eigenstates, these chi plus and chi minus should be orthonormal. So the normal part of orthonormal means that the inner product with itself should be 1. But and then the orthogonal part, the ortho part, is that two states that are different are going to have an inner product that vanishes. And so this should be 0, and this should be 0, and this should be 1, and this should be 1. And that's good because what it means is we're left with just a squared times 1 plus b squared times 1, or it's a squared plus b squared. And we want that whole thing to be equal to 1. And there it is. And so this has that familiar structure where if we expand our general state in, come on. All right, I'll leave it like that. If we expand our general state, chi at the top, in terms of the eigenstates of the spin operators, then the coefficients a and b, if you take the absolute square, they tell you the probability that you're in the spin-up state is a squared, and b squared is the probability that you're in the spin-down state. All right, good. So I want to continue with this idea here. And what I'd like to do next is let's consider the expectation value of s squared, the expectation value of s squared for a general spin state pi. Okay, so what we have to calculate, if I want the expectation value of s squared, I have to do the inner product between chi and s squared acting on chi. Okay, well, that's fair enough. it's actually very similar to the sort of thing that we just did to show that a squared plus b squared would have to be equal to 1. So we'll just repeat that. So we get a star, then we have our spin up state plus b star, and we get our spin down state. Then we have our operator, s squared, and then we have spin up plus the spin down part. Okay, now I know that we could just write down this answer pretty quickly because we already know the eigenvalues of s squared acting on these states. It's h bar squared, s times s plus 1. But what I'm going to do for just to help us understand a future step is I'm just going to write out all these terms. Okay, so what are we going to get? We are going to get a squared chi plus s squared chi plus. So we get a squared chi plus s squared chi plus. Okay, then we get a star b, and we should have chi plus for a star. We have our operator, and then we have chi minus for b. Then we should get, let's see, a b star. A, we'll get a chi minus for b star, s squared, and chi plus for a. And then lastly, we should get b squared. So it should be chi minus s squared, chi minus. I think that's probably right. So I'm going to call this 1. All right. So if I wanted to find the expectation value of s squared, or in fact any other operator, I would just have to evaluate all these inner products. Now I know that s squared is an eigenfunction of these chi minus and chi plus states, and so clearly this one's going to vanish, and so will this one. But in general, this is the procedure that you'd have to follow. So finding the expectation value of s squared requires evaluating 4 inner products. It is often convenient to define a matrix representation of our general state and of our operators, s squared or sz or whatever that we're doing. Now, we've done this once before, but we haven't used it much. And so what I want to do is I want to just kind of go slowly through this and just see how this works. What we're going to try to do is we're going to come up with a nicer way of getting 1, which we already know is how we would have to calculate these expectation values. Okay, so let's just consider an ordinary vector. So I'm going to say some vector v is a I hat plus b j hat plus c k hat. Okay, nobody would object if I said, well, I could represent that vector as a column matrix and I'll write it as ABC. I just take the coefficients of my 3 basis unit vectors and I just put them in this column matrix. Okay, but I could do this, I could write this in a more interesting way. I could say, or let's say more revealing way, maybe. How about that? Let me write this as A100 plus B010 plus C001. Now, it's pretty clear that this column represents our unit vector I hat. So this is like our I hat, and this is like our j hat, and this is like our k hat. So what I want to do is I want to do something similar for our eigenstates. Okay, so what I would like to do is to say, all right, so if our general spin state is A times the spin up eigenstate plus B times our spin down eigenstate, well, I want to write chi as a column vector. And all I'm going to do is I'm going to take the coefficients of the eigenstates and make a column out of them. So these basis eigenstates are like the unit vectors that we're familiar with, and they have all the same properties. They're normalized, their length is 1, just like our unit vectors have length 1. They're orthogonal. If I take the inner product between these two, it'll be 0 unless they're the same state. Same thing. If I take the dot product of I hat with j hat, I'll get 0. I only get non-zero when I take I hat with I hat or j hat with j hat. So the analogy is very good. So then what I could do is I could say, well, let me write my spin state as a column vector, and I'll write it as A times B. Or if I expand it out, I could write this as A 1 0 plus B 0 1, where the 1 0 is like my chi plus spin state. It's the column vector representation, column matrix representation of chi plus. And 0 1 is the column matrix representation of my spin down state. Okay, good. So let's just emphasize this one more time. So the column matrix representation of spin state chi is, okay, it's equal to AB. And so this A is the coefficient of basis state chi plus, and the B is the coefficient of basis state chi minus. All right, fair enough. I could also do like a row matrix representation. So the row matrix representation of chi. So take the permission conjugate means I have to take the transpose and the complex conjugate. And so that is just the adjoint, which is going to be a row vector. And the elements are going to be the complex conjugate of A and the complex conjugate of B. So you could see, probably without actually writing it down, if I was to take chi adjoint multiplied by chi, I'm going to get A squared plus B squared. That has to be 1. That's the normalization requirement. Okay, good. So that's the kind of column and row matrix representation of an general state. What we have to do now is come up with our square matrix representation of operators. So the idea behind the matrix representation of an operator is to, if you like, this is This is how I like to think of it. So you can decide if it helps you. We're going to try to pre-compute all of the inner products needed to evaluate s squared. Okay, let me remind you of this equation one here. Equation one, we calculated the expectation value of s squared using the really standard method, and we found that in general, for our basis that has only two states, we have to calculate four different inner products. All right. So we're going to try to build a matrix that has these inner products as their elements. All right. So the definition is the mnth entry of our s squared matrix is going to be the state im. And then we have s squared, and then the state chi n, where for a spin 1/2 system, let's say, m and n can be either plus or minus, right? So we could have chi plus or chi minus here, and we could have chi plus or chi minus here. All right. So let's write down our s squared matrix. All right. So what I'm going to do is I'm going to put the 1, 1 position. I'll have chi plus, chi plus. Okay, so we have chi plus, s squared, chi plus. And then in the 1, 2 position, I'll have chi plus first, then our s squared, and then chi minus. And then in the 2, 1 position, we'll have chi minus, s squared, chi plus, and then lastly, we'll have chi minus, s squared, chi minus. Okay, so let's try then this way of calculating an expectation value through matrix multiplication. So that is, we're going to find the expectation value of S using matrix multiplication. You know, we're not really getting away from evaluating inner products. We've just stored them inside this matrix. But let's go ahead and let's just multiply this out. So what did we say? We said the chi dagger was going to be A star, B star. And then we have our S squared matrix. Okay, so we're going to have to write it all out again. That's fine. So we have plus plus, plus minus, minus plus, and then minus minus. Okay, and then we still have our chi column matrix AB. All right, so we're trying to show that this is the expectation value of s squared, and I just realized this has to be an s squared. Okay, so we'll first do the multiplication here and here. So we'll have still our A star, B star, and then, okay, so let's just grind through it. So it's A times this plus B times this. So we're going to have in our first row A chi plus s squared chi plus. And then still, this is still the same entry. So we're going to have plus B chi plus s squared chi minus. Okay, so that's the first row. This is 2 by 2 times 2 by 1, so we should get a 2 by 1 out. So we'll get a column matrix after this multiplication. So then again, we're going to have A times this plus B times that. Okay, fair enough. So A chi minus S squared chi plus, I think, yeah, plus B. This should be minus minus. All right. And now we're going to have, let's see, a 1 by 2 times a 2 by 1. So we'll just get a number out. That number better be the expectation value of S squared. All right. So let's see. We're going to get A star times this plus B star times this plus this. Okay. So it's A squared chi plus S squared chi plus. And then we have, let's see, A star B. A star B chi plus S squared chi minus. It's a lot of writing to prove a point that I think we can all see already, but let's just finish it off. And then B star times that. So we're going to get B star A chi minus S squared chi plus B squared. Chi minus S squared chi minus. Okay, and this we'll call 2. And if you look back, equation 1. A squared plus B squared minus minus. And then the ones with a mixture of A and B have a mixture of plus and minus. And we have the exact same thing here. A squared plus B squared minus minus. Mixtures have mixtures. So this is identical to equation 1. So this is identical to 1. And so that suggests that our matrix multiplication is equal to the expectation value, which is equivalent to our standard way of calculating expectation value. So this is the matrix representation. The matrix representation is especially nice for spin states, spin 1/2 states, especially because there's only 2 eigenstates. And so you're only going to ever be dealing with 2 by 2 matrices and columns of only 2 entries. And that's quite easy to deal with. Now, we could go back to some of these matrices and say, well, look, I already know the eigenvalues of S squared acting on these eigenstates. And so we could simplify significantly what we've written here. And so let's go ahead and do that. So how are we doing here? Okay, so of course, the inner products in the matrix are easy to evaluate since chi plus minus are eigenstates of our S squared operator. All right. So for spin 1/2, S squared acting on chi plus minus is, well, the only difference between chi plus and chi minus is the value of m. M could be plus a half or minus a half, but s is always 1/2. And so this is just going to be h bar squared 1/2, 1/2 plus 1 times chi plus minus. So this is s equals 1/2. But 1/2 plus 1 is 3/2, and 3/2 times 1/2 is 3/4. And so we get 3h bar over 4. Sorry, it's an h bar squared. 3h bar squared over 4 chi plus minus. All right. So therefore, the matrix representation of s squared is determined, or is, I could just start, is. Okay, so s squared. I guess I'll write it all out again. So we're going to have chi plus s squared, chi plus s squared, chi minus s squared, chi plus chi minus s squared, chi minus. Okay, so every single one of the s squared, whether it's acting on chi plus or chi minus, is going to result in 3h bar squared times 4 times whatever the eigenfunction was. So that's a constant. It comes out. So we'll get a 3h bar squared over 4. And then we're going to get chi plus, chi plus. Well, if they're normalized eigenstates, that gives a 1. And then I get a chi plus and a chi minus. Those are orthogonal, so we'll get a 0. Minus and plus is orthogonal, so we'll get a 0. And then minus and minus, normalized, we'll get a 1. And so this is our s squared operator in matrix form. So this is the matrix representation of our s squared operator. Okay, let's check it. Let's check s squared chi plus in matrix form. So we just wrote down the matrix operator. I mean, it's fairly obvious. This is the identity matrix, isn't it? So it doesn't matter what kind of column matrix I put here. I'm just going to get that column matrix back again. And so this is going to be equal to 3h bar squared over 4, 1, 0, which is the same thing as 3h bar squared over 4 chi plus. And there's our eigenvalue equation worked out using matrix algebra. There's the eigenvalue. This is equivalent to s times s plus 1 times h bar squared. Okay, so we could do the same thing for our sz matrix. So matrix representation of sz. Okay, well, we'll just write it out. There's nothing like writing out the details to make things clear. It just requires a willingness and an investment in time to do it. Okay, this is going to be a chi minus sz chi plus chi minus sz chi minus. All right. Well, this is the spin-up state. It has m value of plus a half. Sz, acting on this state, has an eigenvalue of h bar times m. So here, we're going to get h bar plus a half. This is, well, it's plus a half times h bar. This one is going to be minus a half times h bar, minus a half times h bar, plus a half times h bar. It's just that this is going to vanish, and this one's going to vanish because these are orthogonal. And so we end up here with h bar over 2. Here, we're going to get minus h bar over 2. This is because m is equal to minus a half for chi minus, and this is m is equal to plus a half for chi plus. Over here, we're going to get 0 and 0 because we have orthogonal basis eigenstates in those positions. Okay. And so we end up with our sz in matrix representation is h bar over 2, 1, 0, 0, minus 1. Okay, good. So there's something important to recognize from what we've done so far. We've done 2 different operators in matrix form. We've done s squared, and we got a diagonal matrix. We've done sz. Come on. There we go. And we got a diagonal matrix. So whenever you have a whenever you have a set of eigenfunctions that are, sorry, what do I want to say? When you have an operator that has a set of eigenfunctions and you construct the matrix representation of that operator using its eigenfunctions, you get diagonal matrices. And those diagonal matrices are extremely nice to work with. Okay, so let's see some counterexamples where we're not going to get diagonal matrices. Okay, so what do we know? We know that S plus acting on the spin down state is going to take our M and it's going to increase it by 1. So if we have M is minus a half, it'll become M is plus a half. And it increases the eigenvalue by h bar. So we get our h bar, and then we get chi plus. Same thing, if we had the lowering operator and it's acting on the spin up state, it takes m and brings it down from plus a half to minus a half. Okay, but if I try to take my raising operator and I act on the spin up state, m plus a half is the highest spin z, the sz state that we can get. So I can't go any higher than that. And so I have to get a 0. And likewise, I can't lower the spin down state any lower. All right. So we calculated something at the start of the class. And we calculated that so that we could use it now. What I want to use is S plus acting on state SM. Sorry, there's a bit of a lag here. I'm going to see if I can speed this up, make this more responsive. All right. Where were we? Here we are. Okay, so, oh, this is much better. Oh, sorry, it's better for me. maybe not for you. S plus 1. For the projector, this might be not an app problem, but a Wi-Fi problem. Okay, so this is going to take us to S and M plus 1. Okay, so this is what we did sort of right near the start of the class. And so I want to take a particular example. Let's take S plus acting on, I mean, really, all we can do is we can act on the spin down state. I can't do the spin up state because I'm just going to get a 0. So let's try it and let's see what happens. We get H bar. And then let's see, S is always a half. So this is 3/2 times a half. So it's 3/4. So we get a 3/4 here. And then we go minus. And then let's see, M is minus a half. Okay, so this is going to be, I have to do it slowly. Otherwise, I'm going to screw up the signs. So it's minus a half. And then it's minus a half plus 1. And so that's plus a half. Okay. And then this is going to go 1/2. And then minus a half plus 1 is plus a half. So we get plus a half. Oh, shoot. Plus a half. Okay, let's think about this. These minus signs cancel. So this is 1/4. So this is 3/2 plus 1/4. So what does that come out to be?
5/4.
5/4.
Oh, sorry,
No,
7/4.
7/4. Yeah, that's not what I wanted. What have I done wrong? Minus 3/4. So where? Oh, 3/4. Yes, you're right. Yes, that is my mistake. Thank you. There we go. That's what I wanted. 3/4 plus a quarter is 1. That's what I was hoping for. Thank you. Good. So this is H bar 1/2, 1/2. All right. Perfect. So now what I want to do is I want to construct the matrix representation of S plus. Yep.
Why did we pick S plus and S minus so that they had an eigenvalue of H bar instead of like 1, so they just directly raised the word?
Because that's what we did last time. So we saw that the raising operator increases the Z component of the angular momentum by H bar. So that's from a couple classes ago. So if you review the notes, I think you'll find that there. Yeah. Okay. So let's see. We want to do chi plus, S plus, chi plus, chi plus, S plus, chi minus, chi minus, S plus, chi plus, chi minus, S plus, chi minus. All right. Good. Now, a bunch of these we could get rid of right away. We cannot raise the spin up state. So 0, 0. Okay. Now, if I raise the spin down state, this is going to become chi plus. And then we're going to have a chi minus inner product with chi plus. And that's going to be 0. So this is proportional to, well, I don't have to say proportional to, I could just say this is H bar chi plus, and all together, that's going to be 0. This is the only one that's not 0. So this one is going to be H bar chi plus, and then we're going to get chi plus, it's going to be a 1, and it's going to leave just the H bar. And so we're going to get just H bar here. And so our S plus matrix representation of that operator is 0, 1, 0, 0. So the chi plus and the chi minus are not eigenstates of the S plus operator. And when we worked out its matrix representation, it is not diagonal. So we get diagonal matrices only when the operator is acting on its eigenstates. Okay, you could do the same sort of analysis for the S minus state. And what you'll find if you do that, I mean, we could kind of do it in our head. Just imagine these are all S minuses. Well, S minus, we can't lower these, so we're definitely going to get zeros here. When I lower this one, it's going to become chi minus, and it's going to vanish when I do the inner product with chi plus. So that's going to be 0. I could lower this one, and then I have chi minus, I get a 1. And so there are our raising and lowering operators represented as matrices. Okay, how are we doing here? 4 minutes. All right. So we'll do one more thing, and it'll be almost trivial. Well, it will be more or less trivial, and then we'll finish for today. Finally, let's use what we know now for our raising and lowering operators, and the fact that that is equal to Sx plus or minus Isy. So what does that mean? That means if I was to take the sum of S plus, the top sign, plus S minus, the bottom sign. Well, if I added those S plus and S minus, the imaginary term Isy is going to cancel because one time it's plus and the other time it's negative, but the real term is just going to add, and we'll get 2 x. Okay, and so that means Sx is 1/2 of S plus S minus. Okay. Well, I have S plus and S minus right there. And if I add them up, I'm just going to get 1, 1. I have to have a factor of 1/2, but that's fine. So I get h bar over 2. Whoops, that's wrong. 1, 0. Okay, and lo and behold, again, S squared and Sz have common eigenfunctions. When we build matrix representations of those operators using those eigenfunctions, we get diagonal matrices. S plus, S minus, Sx, and we're going to do Sy. They are not operators that have those same eigenfunctions. And when we build their matrices using those eigenfunctions, we get non-diagonal matrices. Okay, S minus. So that's Sx. So we can put a box around that. And then the last thing we'll do is say, okay, S plus minus S minus. What would that be? If I took the difference between these S plus and S minus, the Sx will cancel. And then we'll get Isy minus Isy. So we get 2Isy. 2Isy, or Sy is equal to 1 over 2I. Or in fact, maybe I'll write it as minus I over 2 S plus minus S minus. That's equal to h bar over 2. Okay, so the first thing here, we can get these matrices back on the screen. All right, first thing I'll do is take a difference. And so I'll get 0, 1 minus 1, 0. but then I'm going to multiply by a minus I. So we'll get 0, I think, minus I think, and then we'll get plus I down here, and we'll get 0, and that's our SY. Okay, so this is quite a convenient place to stop, actually. We have defined the matrix representation of all of our spin 1/2 operators, S squared, Sx, Xy, Sz, S plus, and S minus. And what we'll start doing is we'll start using these to solve some problems involving the spin of an electron. All right, thank you very much. Have a good day.